So let's look at the definition of an inverse function. So we can see here that an inverse function is two functions f and g, where if we input g into f, we get x. And if we input f into g, we also get x, okay? For every x in the domain of g and for every x in the domain of f, okay? And so we call those inverse functions, and we denote them by this notation, right? And again, it's not an exponent, even though it is in the place of where an exponent is generally in math, just in the same way that f of x doesn't mean f multiplied by x, right? So it's just something you have to remember. In the case of function notation, some of that is a little bit different in terms of the operation. It's not an operation, it's a notation that represents, in this case, the inverse function, okay? All right. And so here they show us what we just looked at with the two functions we looked at a minute ago, where if we input f inverse into f, we get x, and if we input f of x into f inverse, we also get x, okay? So the domain of f must be equal to the range of f inverse, and the range of f must be equal to the domain of f inverse. So again, just like we saw before, the domain and the ranges flip, right? Where the domain of f becomes the range of f inverse, and the range of f becomes the domain of f inverse, okay? All right. So when we look at inverse functions graphically, what happens is they are symmetrical about the line y equals x. So when we swap the input and output values, if we swap AB with BA, then we see that those points are, again, like reflections across the line y equals x, okay? So they're directly across, perpendicular at the same distance to each of those points, all the corresponding points. So if you were to plot any point here, it'd be directly across the line y, y equals x, okay? And so that's in terms of graphically what's true about inverse functions. So that's one way to kind of recognize them graphically, is to see if they're symmetrical about the line y equals x. So if you drew a diagonal line, that, remember, that's the identity or the parent function of linear functions. If you were to draw that diagonally through the graph, through the first quadrant and the third quadrant, and fold along that line, then inverse functions should mirror or match up on the each side of that fold. So here's a specific example of f of x is 2x minus 3, and f inverse of x is 1/2 times the quantity of x plus 3. And you can see here's the line y equals x, and you can see both of these linear functions graphed, right? And you can see a bunch of points plotted as well. So you can see that 1, 2, the inverse corresponding points is 2, 1. 3, 3, and 3, 3 are the same, right? Because if you swap the domain and range, they're the same. So that's where the lines actually intersect, right? Then you have -1, 1 mirrors to 1, -1. -3, 0 mirrors to 0, -3. -5, -1 mirrors to -1, -5, and so forth and so on. But you can see that all of those are directly across at the same distance, directly across the line y equals x, right, at the same distance. All right, and so that's just a kind of a visual of a point for point kind of situation where you can see the map across the line y equals x. All right, so graphically, for a function to have an inverse, it must pass actually the horizontal line test. So remember that all functions pass the vertical line test, right? So they have to, if you draw or take a vertical line and scan it across a graph, then it can only cross at one point, right? It can't cross at more than one point, or else it's not a function. For a function to have an inverse, because not all functions have inverses, but for a function to have an inverse, it must pass the horizontal line test, okay? So it must do the same thing with a horizontal line, where you could draw a horizontal line anywhere on the graph and it can only cross once, okay, no more than once. And so this function here on the left, which is x cubed minus 1, it does pass the horizontal line test, right? So this would have an inverse, okay? Whereas a parabola or quadratic function, if we were to draw a horizontal line, you can see the one here, it would cross at 2 points, right? And there's a few of those that we could draw that would cross at 2 points. And so that means that this one does not have an inverse, okay? So if I were to try to find an inverse of this function, I wouldn't be able to. And then you can see this one here's this is a reciprocal type function, and in this case, it does pass the horizontal line test, right? If we drew a horizontal line anywhere, there'd be nowhere where it crossed more than once, okay? And so this one would have an inverse. All right, and a function that does pass the vertical and horizontal line test, we call that a one-to-one function. So a function that passes the vertical and the horizontal line test is called a one-to-one function, and that's a function that can have an inverse, okay? So function f has an inverse if and only if it is a one-to-one function. So if it's a one-to-one function, it'll have an inverse, and if it has an inverse, it has to be a one-to-one function. Okay, so remember that's what if and only if means, is the conditional works both ways, okay? And so a one-to-one function, again, graphically is a graph function that passes the vertical and the horizontal line test for every point in its domain and range. And then if it is a one-to-one, it has an inverse. And remember, if it has an inverse, then it has to be a one-to-one, okay?